Professor Zou Xiaoxin, who is from Jilin University. He's going to talk about the status quo and the prospect of development of key materials for PEM electrolytic water anode. Experts and friends, ladies and gentlemen, good afternoon. My name is Zou Xiaoxin. I'm from Jilin University. Today I'm going to talk about PEM electrolytic water anode, key materials, prospect, and status quo. I listened to Professor Chai's presentation. I think it was an excellent presentation. I learned a lot from him. I've taken down a lot of notes. But his presentation touches more on the overall picture of the industry. But my speech is going to focus more on the niche market, PEM technology, and in particular, our understanding, our technologies regarding PEM electrolytic water anode. A lot of speakers already talk about the carbon neutral and carbon peak goals. China already has our own goals. In addition, we're joining the rest of the pack in the international world. If we can produce hydrogen with renewable energy sources, it's possible for us to get the hydrogen cost down to a comparable level with production of hydrogen with natural gas. So or hydrogen production by electrolysis from renewable resources and sources represent an important direction. As was mentioned by Mr. Chai, there are two commercial electrolysis technology. One is alkaline electrolysis technology, and the other is PEM. For the first technological pathway, its advantages are technology is mature, cost is low. However, PEM technology has such advantages as high current density, high energy conversion efficiency, high hydrogen purity, fast response, and more matching with wind and solar. So according to some market forecasts, with the market of electrolyzer fastly grow, the PEM market will also grow and the cost will go down. Internationally speaking, ITM Power, NEO, and Siemens were some of the first companies to study PEM electrolyzer, and they have already applied a lot of PEM electrolyzers and stack. Compared with them, China-wise, we only have a couple of companies that are smaller in size, and the technological accumulation is less solid. The Chinese companies are represented by SPIC, CSIC, and Sakisasi, as well as Dalian Chemical and Physical Institute of the Chinese Academy of Sciences. Compared with alkaline electrolyzer, PEM is more complicated structure-wise. It contains a lot of components from the very left. This is a single electrolyzer. As you can see, you have this cathode transport layer, and you have the membrane electrode and an anode transportation layer, as well as two more plate type.
So all these components, like the hydrogenation solution, oxidation solution, and also the PEM, and all these are very important. So since the anode is in a high oxidation and a high corrosion condition, so it needs the iridium, and it also needs other materials to improve its surface, to strengthen its surface to have the corrosion-resistant properties. So to the anode materials, we most import or procure from the overseas. The catalyst relies on the iridium dioxide, and we also know that iridium is very expensive and its performance needs to be improved. The second is membrane electrode, and in this electrode, the content of precious metal is still too high. Although its capacity is high, the cost is also very high. Then in terms of a porous transmission, we need to still improve its fluid field performance and also to improve its anti-passivation treatment. So for us, what's crucial is to develop high performance and low cost domestically made key materials. We also agree that we can also say that in the past 10 years, we are focusing our research work on the anode material. And as I said, it is in a high oxidation and high corrosion environment. So many of the components is prone to corrosion. So for the past many years, we are developing the materials that can be more stable in the extreme conditions, as I mentioned. So next, I'm going to talk about how we develop this new type of anode materials. Well, let's first of all talk about iridium catalyst. So from the chemical point of view, it is a iridium dioxide material. So in the battery pile level, it takes about 30% to 50% of the cost. So from another side, you can see that the catalyst, the iridium dioxide, still is not very active as a catalyst. Also, it is a very scarce resources, and it is one. It only takes. It is only 1% of the total reserve of platinum, and the cost is 5 times that of platinum. So in the future, we want to introduce in the low cost and high and also low capacity iridium, and that will really help us to improve our process. So then I am going to tell you what we have done in our lab and how it can improve our work in the anode material research. So first of all, in terms of the crystalline structure, well, in the past there is this very important founding. So in 2016, the U.S. scientists found that using the beam epitaxy is able to have better reactions in the electrocatalysis, but this thing has to be grown in vitro, and it uses the element strontium, and this, although has a very high catalyst performance, but it is in the metastable phase. So is it able to be synthesized without a base? And the second thing is that the SRIRO3, what about its activity of its crystalline phase, and what about its stability? We still need to make further research into that. And after many years of research, we start to be able to synthesize the SRIRO3 structure. So we found that all of the sides are coplanar connection. And if we look at the inorganic chemical point of view, then it's really rare. So we are actually the first example that have this coplanar connection. So with this coplanar connection, no matter in terms of activity or the stability, it is much better than the iridium dioxide, and also it's better than 3C SiRO3. In about 5 years later, we developed an NBO topology structure catalyst. It has a very low density skeleton, and activity is higher than the previous generation. Well, I just give you an example of the metal structure. And just yesterday, I got a question whether theories is able to guide our research and development, and whether it is able to solve the problems. Well, the theoretical calculation, to some extent, it is able to guide us, but if it is in the complex structure, it is really difficult to target at the precise the problem we are having now. But still, the theoretical calculation can provide us some guidance in the general way. As I mentioned, we need to improve the activity of the iridium, and on the other side, we need to reduce the use of iridium. So how to do that? Well, we need to introduce in a non-iridium element. Then what element can do that? Well, through the calculation, we can find the element we need. Through our calculation, we calculated the pull-by diagram of all the elements in this table of elements. You can see that apart from the precious metal, only the green ones highlighted here are able to resist the high voltage and high acidity. So if we are able to produce the catalyst to replace the use of iridium, then we can only choose from these elements. So theoretically, we are able to build this model. We can produce the iridium dioxide and titanium dioxide into the solid solution. And the structure is rutile or anatase or brookite. As long as the titanium dioxide form the solid solution, then the iridium site has a very high activity. It is higher than the iridium dioxide. So this really reminded us that if we're able to make a iridium dioxide solid solution, then we can produce a highly active catalyst. Then where does this activity come from? If you look at the structure of the solid solution, you can see that in the iridium site, the oil and the oxygen absorption power is pretty balanced. So if we are able to make the solid solution, then we can produce a highly active catalyst. I have said that. But the problem is it's a metastable phase. So in terms of the thermal perspective, it is not stable. And so how to achieve our final goal? Well, what we do is we want to combine the strontium titanium trioxide solid solution and combine it with the titanium iridium dioxide solid solution. And we also find that with the calculation to these different layers of titanium dioxide, and also by calculating the proportion of the atom number of titanium and iridium, then we can produce such a catalyst. And through this chart, you can see with the reduction of 57% of iridium atom, we can actually improve the activity by 34 times. So this is one way we can achieve that. We can also improve its components in this way. So there are many ways, and we can also improve the bond to improve the activity of iridium. In terms of application, in the past 10 years, our team has produced a series of iridium-based catalyst, and this we have formed such a large portfolio. So there are there are iridium dioxide catalyst or the IR ruthenium oxide. So we want to take the first product as an example. This is iridium black. So iridium black is like this. So some iridium black is very electric conductive and others is not as much. So the reason why is because first of all, you need to ensure the dispersion of the nanoparticle of iridium, and also you need to make sure that this particle is suitable for the water electrolysis. And in our lab, we can balance these two features. So the conductivity is about 5 to 7 Siemens square centimeters. And this year we are also working with China Petroleum in the pilot testing and evaluation. So in terms of activity, it is meeting the target, and it can perform stably by in 1,500 hours. And this year we're also going to use it in a battery pile. So in the memory electrode, the iridium capacity is still very high. In order to reduce the capacity of iridium, very recently we developed a structure. It's very porous. The pore density can be over 74%. It is highly porous, and structure with a large content of cavity. So with this structure, we can improve the capacity. We can reduce its we can improve its activity, reduce its capacity, improve the stability. And so far, we have tested over 2,300 hours, and it performs well. So apart from iridium black and the iridium dioxide, there are other possibility. So no matter how you change the structure, the capacity of the iridium has a limit. So that's why we are also developing the carrier material. No matter if it's the iridium particle or the other particles, we need to develop a carrier for improving its good features. And we can see that in the structure, the different particles is interconnected. By combining these connectivity and by producing such a carrier, we can also reduce its capacity and improve its activity. And its membrane electrode performance is 2 voltage at 3.6 A per square centimeters at 80 Celsius degrees. And another possibility is to develop the porous transmission layer. And the most used is the titanium fiber cloth. So there are a few problems with this technology. One is the transmission rate of fluid is pretty low, and the second is the contact rate with the catalyst layer is pretty low. So what we do is we have developed this very new type, straight pore structure. So you can see from the left-hand side, this is a photo of the traditional titanium cloth, but with our technology, if you put it under light, you can see that the light can come through and the fluid can also come through. There are many advantages in our technology. First of all, it can reduce the path or length of the fluid. It can improve the exchange of gas and water, and it can also improve the contact with the catalyst layer. It also have the anti-tensile capability compared with the traditional PEM membrane. And you can see this is the resistance power of our new technology.
Including our material is of better permissibility compared with the felt, and our straight-through multiple transmission structure layer has a more advantageous property. Its property-wise is more comparable with carbon paper. So given the transport layer that we developed and our low iridium catalyst, let's take a look at some of the key figures in electrolyzer. One is the precious metal loading on the part of the membrane electrode, represented by the horizontal axis. The lower the better, and the vertical axis, the density, the lower the better. So be it in the America or in China, be it we are talking about DOE indicators or Chinese indicators, the goal is to come closer to 0.0. And in 2023, the loading is 1 milligram per square centimeters. As for current, it should be 3.0 amp per square centimeters. And there are only a few players who's capable of attaining this goal. We are very fortunate that 3 of our catalysts are able to fall into the category, and potentially we have 2 more to reach the target for 2025. So on the whole, in terms of PEM water electrolysis, anode catalyst, basically there is a consensus in the industry. Firstly, whether iridium can be replaced, the answer is no. Iridium cannot be replaced. That's the answer to the first question or concern. And second, we try to minimize the use of iridium in China, in Europe, or in America. People are working to people have this pathway to bring down the use of loadings of precious metal. In addition to loading requirement and activity requirement, for PEM electrolyzer, there is an indicator for life, which is around 80,000 hours. Be it in China or outside China, we haven't seen any reports of PEM electrolyzer that is even near the target of 80,000. Most of the products are in the range of thousands of hours. So for low loading, high activity, and long life PEM electrolyzer, there's still a long way to go. We have a lot to do in order to develop such a catalyst. A few words in summary regarding the anode catalyst. There are several things we can do. We need to have the synergy of conductivity, activity, and stability. Why I'm putting conductivity in the very first place is because in catalyst there is the triangle stability, activity, and selectivity. However, if you want to develop low iridium catalyst, conductivity is our first consideration, without which we don't actually need have the need to consider any other factors because they're just not relevant. And the second is anode iridium loading technology in order to turn it into low loadings of noble metal. And the loading on the part of anode is key because on the part of cathode, we have already reached the ceiling 0.2, 0.3 milligram per square centimeter. However, in China, at the anode level, mostly are above 2 milligram, and sometimes the figures are as high as 3, 4, or even 5 milligram. So there's a lot of things we can do and need to do. In terms of the transport layer, personally speaking, in terms of the porous structure, we have the irregular structure formed by carbon felt, and we have seen the transition towards the straight-through pore structure. So that shows in optimization. And also we need to reduce the thickness of the surface coating layer, the precious metal coating layer. In the future, there might be technology to reduce the coating layer as well. Thank you very much. Many thanks to Professor Zhou. Professor Chai devoted his entire life to developing catalysts, and Professor Zhou has spent 10 years focusing on the carbon, on the market, on the PEM market. So congratulations on his achievements and look forward to more success from his research.